Thank you very much, Chairman. So, indeed, the topic of my presentation is on the influence of the crack length and the maximum stress on the crack growth rate. And I'm from the Netherlands Aerospace Center. So the problem for most graphs presenting the crack growth rate versus delta K is that there's much scatter in the graph or in the data. And it's usually fitted after that with a function which has a single exponent in the region 2, so that's the Paris region. However, the fatigue crack growth curves typically show multilinear behavior, which is related to different micromechanisms of crack growth, for example, along crystallographic planes in stage 1 and more ductile with striations in stage 2. So here you can see that it was already reported in 1979, again by my colleague Russell Onehill in '88, and also Jim Newman reported it frequently, that there's a multilinear crack growth rate. So what did we do to investigate this and then to solve this problem of the noise in the data? So we did constant stress range crack growth rate test on 7075 materials, T7, on 160 millimeters wide MT specimens. We pre-cracked those specimens to 2 millimeters single side with the same test parameters, and we measured the crack length using potential drop. And then we used multilinear crack growth rate to directly fit the crack length versus cycles curve. So we have these points in the multilinear curve, which are the fit parameters. So just as you would fit, you have the fit parameters in a polynomial. These are the fit parameters in our fitting procedure, and you can also regard them as the points in tabular data. If you use tabular data for crack growth, these are the same points there. So here you can see just a measurement. It's not so clear on this one. You can see it clearer on the television, but here is just a line for a single specimen, a crack growth rate curve, and we can fit exactly the crack length versus cycles data using multilinear curve. Here you can see 5 different specimens with different maximum stresses and different stress ratios. So we again can apply for each curve. We can fit directly each curve, and you can see the white line in the curve. It's the fit, and the points, the symbols in the curve are the points where the slope is changing. So we can fit each curve, also at small crack lengths. We can fit it exactly in. So the curves, the colored curves, consist of data points from the potential drop. So it's applicable for multiple maximum stresses and multiple stress ratios. And here you can see the results for these 5 specimens. So each line here is a specimen, and you can see that the curve change at a specific crack growth rate, for example here, for these different stress ratios and different maximum stresses. And if you plot it as function of delta K effective, where we use the Schijve crack closure correction, you can see this curve, it becomes a master curve for multiple stress ratios, and all these points fall closely on top of each other. So we can also use it for deriving long crack threshold data. So we use a very small constant stress range, and just as easily fit the entire graph using our fitting procedure. And we obtain here crack growth data in the threshold without any noise, and it just the white line again. It's exactly following the crack growth rate curve, so you can reconstruct the original crack length versus cycles curve perfectly and get accurate data from that. And this is for naturally increasing delta K testing. So we not have a load shedding so that you have problems with that. So it's natural increasing delta K. We also applied this for different alloys and different heat treatments to see if we can observe differences. So this is the first time that we don't have this noise in the data, and we can clearly observe differences when we do a heat treatment or we change the chemical composition. For example, here we have 25-24 versus 70-75, and you can see in this region, this is region 2, here you can see the change to region 3. The 75 materials of the 2024 and the 7075 have similar behavior here, but when you go to lower crack growth rates and different regime, there you can see the difference between these alloys. And also here in the location where the shear lip develops, there are differences. If you go to the annealed 75 materials and compare that to the T7, you can see that also the crack growth rates are very similar, and then you have a change in behavior at the fourth transition point, and you go exactly over immediately from the fourth, you go to the stage 3 or the region 3 crack growth, where the T7 materials has a additional transition at the T5 and then goes to region 3. So we also applied this to the 775 materials annealed for different maximum stresses and also Inconel 601. And here we observe that we get different crack growth rates as a function of the maximum stress. So we plot here the crack growth rate as a function of delta K, where the maximum stress is included, but still we see an effect of the maximum stress on the crack growth rate. Similarly for Inconel 601, you see an effect, and the effect increases with if you approach the yield stress, for example. So here you can see in this graph, here is the ratio of the maximum stress with the yield stress on the horizontal axis, and here is the crack growth rate for the 775 annealed materials at 12 megapascal square root meter, and for the Inconel 601 it's at 33 megapascal square root meter. And so at this point here, this dotted line, and here as well, you can see that for the low maximum stresses compared to the yield stress, there is an influence of the maximum stress, but it's not so much, and it increases as you approach the yield stress. So if you have the ASTM norm and you see when is it valid, for these delta K values here, the results are valid with for small scale yielding from about these values. So here small scale yielding should be, or it's valid compared to the small scale yielding criteria, while we still see an influence of the maximum stress on the results. So there is a phenomena, and as you can see here, it's also region dependent. So here there's a large difference, but here all the curves are emerging. So it's really also region dependent. So we can also use this fitting methodology on small cracks. So we also observed all these tests were for long cracks, but we also applied it for small cracks on specimens that have 1,000 artificial laser defects of about 50 to 100 micrometers long of deep, and again it is naturally increasing delta K testing, and we applied marker bands, constant and variable amplitude marker bands to obtain the crack growth rates for these small cracks, and also we used the fitting methodology to directly fit the crack length versus cycles curve. So the dots are the measurements of the marker bands, and the black line here is the fit of the A versus N curve, and we can again see a very precise location of the transition point where you go from stage 1 to stage 2A, and here you can also see the long crack data for the same stress ratio. So that was the previous specimen, the previous long crack specimen with the same stress ratio. So here we can see that the transition to a different slope occurs at similar J.Th.M for small and long cracks. Both are at the same stress ratio and the same increasing delta K testing. So there is still a difference between these two. And therefore it's also, so the change in slope is at a similar crack growth rate. So this leads us to a small crack model, which is based on probabilistics. So here you can see a measurement, and there is 1,000 artificial laser defects on such a specimen, and some of them grow a crack, some of them don't, but at the end the lead crack fills the specimen, but there are also other cracks on the same fracture surface. And we also measured the rates at the same crack depth for those defects, and we see that this is the lead crack, so it has a higher crack growth rate already at a crack depth of about 100 micrometers, while others have here again a change in slope, but they have lower crack growth rates compared to the lead crack. So there is a difference, variability in the small crack growth rates on the same specimen. And if you then have a change in slope at a specific crack growth rate, this automatically leads to a change in delta K threshold. So based on a distribution of average small crack, or a distribution of small crack growth rates, in combination with a fixed transition from slope of region 1 to region 2, automatically gives you an apparent change in the delta K threshold. So this is also the physical explanation, in our opinion, for the Kitagawa-Takahashi diagram. So basically it's due to the shift, it's due to the inhomogeneous samples, because we always measure the fastest cracks compared with long crack, which is usually from one notch in the specimen and across multiple grains. And there's also a possible influence from the maximum stress effect. So as you see here, we measured the small crack growth rates at a maximum stress close to the yield stress, and the long crack was measured at 56 megapascal, as you can see here. So there could be also an influence of the maximum stress effect in region 1. So that this could help, but there's definitely, as you can see here, a distribution of small crack growth rates. So we can use this model just to predict the ascent curve, and here you can see our master curve with 55 specimens, long cracks, where we used the delta K effective to create the master curve, and here you can see the long crack data, and here you have our small crack data, which has a shift in delta K threshold, and if we use the small crack growth rates and the defect size that we measure on the fracture surface, so these are iron-containing particles in this alloy, and if we use that crack length, we can obtain the ascent curve. If we use the long crack growth rate, then we get unconservative results. However, we in our measurements we did not incorporate. Yes, okay, thank you. We didn't incorporate the maximum stress phenomena yet, and we measured the crack growth rate at about 300 megapascal. So we are quite good here, but we think that we still need to incorporate the effect to also get more accurate results in the regime near 400 megapascal. So this comes, here we come to the conclusion where we have a look at the effect of crack length and maximum stress. So we see a clear influence of the maximum stress on the crack growth rate in the small scale yielding regime for different alloys. And we also see an effect of the crack length on the results. If we measure small cracks, we get a statistical difference compared to the long cracks, which is more the average effect. So these are the acknowledgement to our partners in the project, and with that, I would like to conclude. Thank you very much.